Okay, guys, tell me everything you know about decoders. So we're starting to deal with our combinational logic circuits. So we started out with the 5 basic gates, right? Learned the 5 gates and then the 10 symbols that we have to represent them. Then we started moving into our combinational logic. And what's combinational logic? When we take the 5 basic gates and hook them up to perform more complex functions, right? You understand? The first combinational gates we looked at were the exclusive OR and the exclusive NOR. But since we use these so much, they have a unique symbol, but they are combinational logic. Then we get into our more advanced combinational logic gates, which is our code converters, our multiplexers, and our demultiplexers. Now, guys, this is not all of them. This is just the beginning of them. We have counters, we have shift registers, we have one shots. We got all neat little things that we can do out of these 5 basic gates. So we have code converters, which are usually referred to as encoders. And then we have decoders, which are code converters. So it looks like if we're going to code something, we need to be able to decode it, right? You understand? And then we get into multiplexers and demultiplexers. So what are decoders? What are encoders? Which will be on this guy right here. And we have 2. So we have encoders and we have decoders. And these would be our code converters. So what's an encoder and what's a decoder? Now watch the lecture. Don't help me out. Act like I don't know. So nobody in the whole class knows what a decoder or an encoder is, of the people who's here. Converts binary into another code. Okay, or into another numbering system. So we have what we call, they called it a 4 to 10 decoder. So this would be binary to decimal, right? You understand? And then we have a 3 to 8 encoder. So this would be binary into what? Octal. And that's the basic ones we have. Oh, and then we have a 4 to 16 encoder, also called a binary to hex, okay, encoder. So these are the primary ones we have. We don't have encoders to go from binary to ASCII and stuff like that. So basically we're going between the main numbering systems, right? You understand? Except for this one. This is not really a numbering system. This is BCD. So this would be 7442. This is the 74 138 rich, and then a 74 154. You can see this guy's going to be big. Because I mean, so we have 4 pins for binary. We have 16 pins for hex. That's 20 pins right there. So this is going to be in a 24 pin dip, which is a big boy. So they maintained this spacing that y'all been dealing with up until they got up to 22 pins. Then when they got up to 24 pins, what they basically did, I guess you'd say it's double the size, is they went to a wider IC. This got us all the way up to 64 pins. This spacing or this size. So here's a 74 154. Hopefully I can find one. Oops, thought I started my camera, but yeah, I did. I don't see it. Oh, I'll be with y'all in a second. Hold on. So this is the package that we're used to right here. This side's right here. This is a 16-pin dip, right? Here's a 74 154. So notice the spacing of the pins are exactly the same as the 14 and the 16-pin dips. But what they've done is they've increased the size, right? You understand? This is a 24-pin dip. This got us all the way up to 64 pins, and that was with the Motorola 68,000 microprocessor. It came out with a 40-pin. It came out with a 64-pin. After that, they decided they could get more pins if they put them in a square and came out the sides. And that way, instead of only using 2 sides, they went to 4 sides. And then eventually they went to a version of what they call a pin grid array. So this is an AMD K65 processor. And they figured out where's the pins at. They figured out they could get a lot more pins if they did what? Just brought them out the bottom. And of course, this has a lot of space in it. Eventually, it got big. And then Intel finally went to a weird microprocessor. I'll see if I can find one. It doesn't have any pins. The socket has the pins. Socket 774. The socket numbers, by the way, are usually numbered by the number of pins. So socket 774 means there's what? 774 pins on that puppy. So they started coming out the sides, then they started coming out the what? The bottom, and then it's basically they're still like this. Your processors now still come out the bottom like this. So, but that's the AMD K65 processor. It's a 64-bit processor, but no, I'm sorry, it's 32-bit. So this is a 4. I'm sorry, I don't want to go off of it. So this is a 4 to 16. This is a 4 to 16 encoder. So an encoder is going to take us from binary to another system, and then a decoder is going to take us from another system back to binary, right? You understand that? Does that make sense? So these things are basically like the, this is, we already went through that. Let's compare. So let's look up the data sheet for a 7442. Where is it going to be at? Well, that's not the data sheet. They might have the pin out, But they're going to be in Blackboard under data sheets. Or I could probably bring out one of those test reference guides, and I'm pretty sure it's in there. Let me get to the right class. 7442. Of course, we understand what the center's letters, so we have a 74LS42 here. So it's a low-powered Schottky. And this is the data sheet. It says it's what? It says it's a BCD to decimal decoder. A BCD to decimal decoders consist of 8 inverters, 8 inverted, and 10 4-input NAND gates. So we're not going to need that. So this is what we got right here. So what you're going to find out is everything from now on is going to be a rectangle. And it's up to you to decipher what it is by the name of the pins or by looking it up. So what we have is anytime you see A, B, C, D on a digital gate, that's usually weighted binary. With D being the most significant bit, D being the most significant bit and A being the least significant bit. And then I've got outputs labeled what? Now this gets people confused because now we have the name of the pin and then we have the pin number. So the name of the pin is out here on the outside on these. So the name of this pin is 0. The pin number is what? 1. Y'all understand the difference? So this gives us a little problem in a lot of times where the name of the pin is a number. So this right here, pin 7 is named what? 6. Yeah, it looks like a 5 to me, but yeah, 6. Okay, so what do these numbers mean? Well, this is a decoder. How many combinations does decimal have? 10 combinations. So notice what happens. So we'll come up here. When A, B, C, D, when they're all low, then output 0 goes what? Low. So it saw a 0 on the input. It saw a binary number that had a weight of 0 on the input, and output 0 went what? Went low. This right here would be a weight of what? 1. See that? So A is low. Now, don't get confused about how they're laid out. So A, if we see A, B, C, D on the names of the pins, A is usually A is the least significant bit, and whichever one goes up to, that's the most significant bit, right? You understand? So over here on the chip, input A is actually pin what? 15. Input B is actually 14. Input A is 13, and input D is 12. So over here I put a 1, so that's a 1, because that's a 1, 0, 0, 0, right? You understand? Or actually 0, 0, 0, 1. And which output went low? Output 1. I come down here, here's a 7, right there. There's a 7, see that? Which output went low? Output what? Output 7. Okay, here's an 8. Right there's an 8. What output went low? 8. So I can look at the outputs and I know what binary number is on the input. Now look what happens when I came over here and put a 10 on there. It says it's invalid, but it's not really invalid. 10 is not an invalid number. It's just this guy's not designed to decode a 10, right? You understand? Or an A. So notice what happens. So if it sees a number it can't decode, then all of them what? Go high. It's not going to blow up. Nothing's going to happen. This thing says they're invalid. But I found out a long time ago that if you have a certain output, an engineer is going to figure out how to use it. I guarantee you. So this guy, if it sees any number between 0 and 9, it has an output. If it sees a number that is not a BCD number, right? So BCD numbers, how far do they go? They go from 0 to 9. If it sees a number that is not a BCD number, then all the outputs do what? Go high. Everybody understand that? So the decoded input, the associated output goes low. So these have low active outputs. How do I know they're low active output? They got the little what? Got the little bubble there. So later on, we're going to learn about something called a
this is what we're going to learn about something called a counter. What do you think a counter does? Counts, yeah. So one of the counters that we'll deal with is a 74, I think 190, 7493 is the one that we're using here, I think. So what I have is I have a counter hooked up to the decoder, and so we can actually see it operate. I'm going to use this simulation called Electronic Workbench, and 7442. So this is 7442. Of course, this could be a 74 LSF42, a 74S42. So here's my counter right here. And to let y'all see it count, I've got LEDs over here. LEDs hooked up to the output. So we'll turn it on. And right now my counter's output no 0. Well, which LED is not lit? 0, because that output is 0, right? A spaceport. So now, so now we counted a watt. This is my count right here, by the way. So, count of 1, which output went up. Okay, so this is a 2, which output went low. Okay, here's a 4. I'm sorry, 3. What output went low? 3. Here's a 4. Output 4 went low. Here's a 5. Output 5 went low. Here's a 6. Output 6 went low. Here's a 7. Output 7 went low. Here's an 8. Output 8 went low. Here's a 9. Output 9 went low. Here's a 10. What happened? Why? Because it's a BCD encoder. So I'm putting an illegal BCD number on there. There's no such thing as a 4-bit 10. It would take 8 bits to represent the number 10 in BCD, right? You understand that? 10, 11, 12, 13, 14, 15. What do you think the counter's going to do? It's going to roll around, right? It'll roll back around to 0, and now we're back and running. See the counter? Later on, we'll get into that, which is pretty neat. But here's the counter. It's got one called QA, QB, QC, QD. Which is the most significant output of the counter? D. What's the least significant? A. So you can see I've got A running over to this LED. I've got B running over to that, showing on that LED, so y'all can see the weights. I got C coming here and D coming there. And by George, they don't put them in the order you think they should be in. They're trying to bring it out so they don't have to cross any wires, right? You understand that? So they come out with whatever pin they're closest to. So it means the way we draw the symbol on the schematic and the way it's actually wired up are two different things. So when we draw the symbol, normally when we draw the symbol, we draw them in line with each other. Y'all got the data sheets? Okay, so if I was going to do the pin out, what would I put over here? Here's the least significant pin. So this would be what? This would be A, B, C, D. What pin would this go to? Right here. What pin number would I put right here for A? 15. What pin would I put for B? 14. What pin would I put for C? 13. What pin would I put for D? 12. What pin would I put for the 0 output? 1. What pin would I put for the 2? For 1, this is 0. What pin would it be for the 1 output? 2. You sure? It's only a 14-pin deal. We got power somewhere. And we got ground somewhere.
No, ground can't be 6. It's either going to be 8. It's a 16 pin dip, right? Yeah, so it's 8. So we go 1, 2, 3, 4, 5, 6, 7. Then we go what? Then does it go 9, 10, 11? Like, huh? Yeah, but normally on the schematics, they don't draw the power pins. They take for granted, if you understand digital, you understand nothing works without power applied. So inside the schematics, they don't draw the power pins. And this gives people problems sometimes because they'll wire up a circuit and don't hook up power, and then they wonder why it don't work. But they don't understand that the power pins are a given, right? You understand that? So when we look at the schematics in the back of the textbook, you'll see no power pins in the whole thing. Because the more stuff you add, the more complicated the schematic gets, right? You understand? So just leaving off the power pins, that's at least 2 pins that we don't draw, but it's understood that that they're what? They're connected, yeah. So this is a 7442. It's a 8 to 4. It's called a 4 to 10 decoder. It's also called a BCD to decimal decoder. Those two terms are used interchangeable. So some data sheets call it a 4 to 10. Some data sheets call it a BCD to decimal. What is it? On y'all's data sheets, I think it's called a BCD to decimal, right? Huh? No, this is 7442. 7442 is a 4 to 10. 74154 is a 4 to 16. Are you okay? So everybody okay on the truth table? This is not a 7442. This must be another guy. How do I know it's not a 7442? Because one thing is 7442 has this, so I'm kind of sorry. I don't know what that one would be. I've never seen that guy. So this decoder, the one they're showing in the book, has high active outputs. So if you look at the truth table here, everything's inverted from a 7442. And why is that? Because the 7442 has low active output. Are you okay? That makes sense? Yeah, and I said that several times. If you look at a chip and you look at the pins and it says A, B, C, that is weighted binary. And A is the least significant bit, and how far it goes up to is the most significant bit. So a 74138 is going to be A, B, C because it's a 3 to 8 decoder. Huh? I don't know what you're talking about. No, this truth table is not for the 7442. This is the truth table for this thing they put in the book, which I've never seen. When you look at the actual truth table for a 7442, which is the one we're going to use, then that's the one we're talking about. Yeah, this guy here, they don't even label A, B, and D. They label them what? Yeah, but if we go and look at all these decoders, so let's look at let's actually look at the data sheets and not the book. Let's look at the data sheets. So we'll go back here and we'll look up 74138. That's a decoder. So 74138, and we'll look at the pin out. And the select inputs are labeled what? A, B, C. So that's 3 bits of binary, which is the most significant bit. C is the most significant bit, and then A is the least significant. And the outputs are labeled. They're labeled Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7. So those are your outputs.
The 7442 labeled them 0. This guy labels them Y, and then but it's still 0, 1, 2, 3, 4, 5, 6, 7 because it's a 4 to 8 decoder. Go to 7447, which is a neat guy. It's 7447. This is a BCD to 7-segment decoder, if it loads. This one's a little different. The inputs are labeled A0, A2, A1, and A3. So you can't, it's not always true, right? You understand that? So there's the inputs on these. You'd bring up somebody else's data sheet, and they might be labeled ABCD. And we'll look at a 7-segment display in a minute. We see these guys all over the place. So we have a 7442. This is a 4 to 10. We have a 74138, which adds a new feature that we've talked about several times, but now we'll actually see it in action. This guy here has enable and disable pins. So we played around with AND gates, right? Using enable and disable, we understand how that works. So let's look at the truth table for a 74138. So we're going to look at the 138, not the. So here's the truth table right here, or what they call the function table. As I find it, it's in here somewhere. Okay, it's right here. So y'all need to go there. Y'all there yet? So when we look at the pinout, I'll go back up to the pinout. We see A, B, C, D. Then we see Y0 through Y7. But right here we got GA, G2A, G2B, G1. And what do they call these pins? Enable. Now what do we mean by enables? If it's enabled, we let it work. If it's disabled, it don't work. Okay. So to enable this guy, what do you think we got to have? G2A has got to be what? See the bubble? Got to be what? Low. G2B has got to be what? Low. G1 has to be high. If any of those pins are not in the correct order, then all the outputs will go high. It will not decode. So to make this thing work, we have to bring these to the right feature. These enable and disable pins were brought about by by computers, microcomputers. So what happens is that everything in the computer has got an address. And then one of the buses on the microprocessor is a bus called the address bus. What do you think the address bus is used to do for? Used to select the thing that the microprocessor can communicate with, or the computer can communicate with. So the computer only communicates with one thing at a time. So whatever it wants to communicate with, it puts a binary address out an address bus, and then we run into special chips we call decoders that actually look at the address. So a decoder would be like you sitting here looking at some lights. This is the address bus, and when all you're set up to do is recognize a certain pattern of ones and zeros. When your pattern becomes ones and zeros, then you reach over and you open up a mailbox. And once the mailbox is open, you can do what? You put stuff in it, or you can get stuff out of it. If your pattern is not on the address bus, then you do what? Your box is closed. So how do we enable these? How do we open these mailboxes, and how do we close them? Well, we open it and close them with these enable pins. So my address decoder would be hooked up to these enable pins. And when the address came out, the address bus that was for this device, what would it do? Well, it would open the mailbox, and it would allow the decoder to work. And that's the way computers work. And people don't understand that. You know, you think your computer is amazing, but it's very simple. Works a lot like our phone system and works like our, how many people can you talk with on the phone at any one time? 3. No, we're not using, you can. We're not using conference calls. Microprocessors don't do conference calls. So one at a time, right? You understand? How do you get to that person? You call their number, right? Inside that phone is a decoder that's looking for your number, right? You're receiving all these numbers all the time. Your phone is receiving all the time. But your phone has a decoder in it that's only looking for your what? Your number. And when your number comes out, how many phone conversations do we have going on here at the same time? Okay, we call that multiplex. Multiplexing is you let multiple devices share the same media at the same time. Well, if we're going to multiplex it, we need to do what? We have to be able to demultiplex it. So how do you demultiplex with your phone? Well, your phone has a number, and you call a what? Number. So that's the way your phone picks out all these conversations that's going in the air. So a media, of course, is what information flows through, right? You understand that? So multiplexing is when we let multiple devices share the same media at the same time. How many different medias do you think is sharing these airways here right now? Several. I wouldn't even know. Any place inside this cell would be sharing our media. Then you got your broadcast TV stations. Then you got all these dang radio stations, right? You understand? All your FM stations out there. They're all sharing this air media. So that's what we call multiplexing. And so multiplexing is what puts it on the media. Demultiplexing is what gets it off, right? You understand? So your phone is a demultiplexer, which is what your address bus is. So using these enable pins gives us the ability to enable this thing when we want to use it and do what? Disable it when we don't. Sometimes we don't. So if I want to use this without using this, I need to tie these 2 pins low, and I need to tie this pin high if I just want to use it without using that feature. So that's what this says right here. So we pick up a new term in our data sheet. We pick up these X's. These X's mean don't care. So if you see an X in a data sheet, it means you don't care. So when this thing is enabled, you don't care what the ABC inputs are. You don't care because the chip don't even look at them because it's disabled. So down here they only show us 2 because so that says G2A and G2B. G2 is equal to G2A and G2B plus G2B. So it says right here if either G2B is high, if either one of them is high, if either G2A or G2B is high, then G1 don't make any difference, right? Your ABCD and your ABC inputs don't care, and all your outputs do what? They go high. If G1 is low, then G2s don't care, because G1 is high active, your G2s are what? Low active. So that means, okay, if G1 is low, I don't care about G2 because it takes all 3 of them to be enabled, right? Okay, if you're disabled, then your inputs are they could be changing, but we don't care what they are, and all the outputs do what? All the outputs go high. So if I bring my G1 high and I bring my G2s low, then notice all the rest of them are in that setup, right? You understand? Then if I put all lows on the inputs, then what output goes low? Y0. If I put a binary 1 on the input, then what one goes low? Y1. If I put a 2 on the input, which output goes low? Y2. If I put a 3 on the input, then which output goes low? Y3. Now what's nice about this is that Octal only uses 3 binary digits anyway, so we can't go over 7. Y'all understand that? But BCD uses 4. So if you put binary, but you got 4, you got 16 combinations, even though BCD is only supposed to use 9. I'm sorry, 10. So you'll see how this guy works? So this is a decoder. So it's taking 3 bits of binary and converting it over to its octal equivalent, right? You understand that? 74154. Right here. This has got a heck of a truth table because it's got 20 pins. So this, by the way, this is how this thing works. But what do you see in that? What gates do you see in that? You see NOTs, right? You see inverters. You see NAND. But I don't care what's in there. Why don't I care? Because you can't fix it when it breaks anyway. I mean, all you need to do, even though it's a combinational logic circuit, has a lot of circuitry inside of it. It looks very complicated, but it's not. It's pretty simple the way these things work. I think the book has a really good demonstration of maybe 2 bits to get an overall feel of how these decoders work. So let's look at these. We got inputs. Where's my inputs? Right there. A, B, C, D, F, A, B, C, D, A, B, C, D. Then I got 2 G inputs. What do you think the G inputs are used for? They're enables. Gate is what they call them. These enable pins are going to be labeled G's, or are they going to be labeled E's, or are they going to be labeled like CS or something like that? These 2 guys are what? They're low active. So you can see right here, if these right here are not low, I can't draw on this. But to make any of these NAND gates over here work, this right here has to be high. The only way I can get this high, can y'all see where the enables are connected to all 16 of these NAND gates over here? You'll see where I'm at. So if this output right here is low, then all the outputs are going to be high, no matter what's on the input. But that's okay. We don't need to know that. We don't need to know how this thing works right there. All I need to know is how this thing works. Right? You understand that? If I know how this thing works and it don't work, then I'll replace the chip. I don't go in there and fix this NAND gate right there. What I like about this is that you can see that it's made up of nothing but what? Our basic gates. But it performs a very complex function. So let's find the truth table on this guy. It's a lot bigger. Let's look at these down here right here at the very bottom first. It says if G1 is high and G2 is low, then what happens? Well, the thing is disabled, so all the other inputs are don't cares. You'll see that? If G1 is high and G2 is low, then it don't care, right? You understand that? So how are we going to make this thing decode? Well, to make it decode, then G1 and G2 have to both be what? Low. Okay, guys, so if I got both of them low, I put all lows on my ABCD input, which output goes low? 0. So it works exactly the same way. You see that? If I put a binary 1 on the input, output 1 goes low. So being low active, by the way, is very, very popular. Can anybody tell me why? Why is most of these guys output a low for a true instead of a high for a true? So this is a true output. So these guys, they're true when they're low. Y'all understand that? So you got to understand true, a high and a low, or a 1 and a 0. And what we're talking about, what's true and what's false. So when I put a 0 on the input, output 0 goes low. So that means the lows are low active, right? You understand? So it means the outputs are true when they're low, or when they're a 0. What advantage does a low output have over a high output? We've talked about this already. Look at my low. Look at that. Look at the low output. So here's my I low out. This is how much current I can get out of this thing for a low. I can get 8 milliamps for a low. Look what I can get for a high. I can get 400 microamps for a high. So all these gates can actually sink more than they can source. So we can get more drive out of them with a watt, with a low, than we can a high. So just about all these decoders are going to have low active output. Because if I want to turn something on, it's better to, right? You understand that? We can get more out of it for a low than we can a high because of that pull-up resistor in there. So let's look at our last. No, that's not a decoder. That's not a. It is. Let's look at this. Y'all understand? We understand. What numbering system do we understand the best? Of all the number systems we talked about, which one do you understand the best? Which one have you been using since grade school? Huh? Not, huh? Decimal number system. We understand the decimal number system. So my computer is a binary device, but I don't. How often do you see binary numbers on your computer? Right, and even then you see hex, right? You understand that even your computer gives you hex because they understand binary is very cumbersome, right? When we get to a lot of bits, so that's why they came out with a unweighted number system called BCD. So we have counters that count in BCD, but the problem is it's still binary, right? You understand? What I need to do is be able to display what number system? Decimal number system. So, of course, they came out. We have indicators that have been around for a long, long time, and these are called light-emitting diodes. Have you ever seen a light-emitting diode? They're called LEDs, and the true symbol for them is like this. And we talked about diodes in the class, right? You understand? But a LED is designed to light up when the holes in the electrons combine at the barrier. They actually emit photons. They actually emit energy. It actually causes energy release. The problem with silicon is that it does not release very many photons, and the photons it releases is at a wavelength we couldn't see anyway. So what they do, instead of using silicon, they use gallium. Gallium releases a lot of photons, but it creates a VF. So the forward voltage drop of a silicon diode is around 0.7 of a volt. The voltage drop of a gallium LED is around 2 volts, but it varies with the color. So that means it takes a lot more energy to cause them to combine. Once they combine, they create a lot of photons. If they put that junction so it's clear in a lens, then you can see these lights. But it only works when they're forward biased. So that means to turn this thing on, I got to make the cathode at least 2 volts more negative than the anode, or make the anode more positive. Now, it didn't take long for them to realize that, hey, we can use LEDs and arrange them into what we call a 7-segment display. 7-segment display. And why they call it a 7-segment display? So they put an LED, and the lens is actually in a bar. Y'all see that? And you can go around these things. So we count the segments. So the LEDs, that would be 1, right? That would be 2, 3, 4, 5, 6, 7. And then normally they have a decimal point. And that's why they got named 7-segment displays. Now what they did was they gave each segment a name. So the names they give the segments, let's see if I still have it up. I don't think I do. Yeah, I do. No, I don't. Or maybe I do. So they named the segments. Can you see the names they give these segments? So the one across the top is called what? A. This is called B, C, D, E, F, and G. And so using those segments, I can display any number in the decimal number system. That makes sense? Now what they say, okay, the only thing we're going to do is turn on segments. So, and I've got eight LEDs because we have a decimal point. Now normally that would take 16 pins, but they realized that what they can do is they can either connect all the cathodes together or they can connect the anodes together inside the chip. So this guy right here, we call it a what? Common cathode. Can you see why? Because it's got all the cathodes connected together. And they call this a common anode because it's got all the anodes connected together. So what we do with the common cathode is we would connect the cathodes to ground, and then I would put a high on each one of the anodes. So common cathodes, we turn those on with highs. Common anodes, we turn those on with lows. That makes sense. Now, the problem we have is that standard TTL supplies are 5 volts, right? You understand? If I put 5 volts across the diode that starts conducting at 2 volts, as soon as I put it on there, it'd blow the LED. So what does that need? What do we need? Start with R. Resistors. We need resistors. So notice on mine, I have one resistor. So this is a common cathode I have up here. So here's my ground, and then I have this coming into the common cathode pin. And then what I can do now, I can come up here, and then I can jump high into here. Okay. Oops, wrong thing, Rich. Okay, here it is right here. So if I come over here and I just push it into these pins, then so now that would be the pin for the what? For the A segment, right? This would be the pin for the B segment. And then I can come around this thing, and then I can come over here and turn on all the segments. See that? One at a time. So if I wanted to display a number, I don't have to turn on a lot of segments. So if I wanted to display the number 3, now the problem we have, now notice this guy here is pretty bright. But as soon as I turn on an LED, then the current flow needed by 2 LEDs is flowing through the resistor, which causes the LEDs to do what? To get dim. So the more LEDs I have lit, the dimmer the display gets. But what I'd have to do is I would have to literally come in here and jump this thing to create the number. If I wanted to create the number 3, it would take a lot of work for me to wire this up, right? You'll see what I'm doing? So what I've got a jumper. I came in here to the A segment first, and I got a jumper going there. By the way, we have the pin out on this thing, but we'll just do it. Okay, so I'll come over here. Let's try this one. Okay, I don't want that one, right? I want that one. And then what would I have to do? I have to jump it. Okay. Don't want that one. Do want that one. And then I would go up here and jump this over to here. And hopefully they'll give me the number 3. Okay. So there's the number 3. That takes a lot of work because I have to do what? And how often do you think we use 7-segment displays? All the time. How many of y'all seen 7-segment displays? Yeah, scoreboards, right? That's big, but you know, your DVD player's got numbers on it. That's probably 7-segment displays, right? Huh? They're all over the place. I mean, these guys are all over the place. So wouldn't it make sense that they would come out with a chip that did the decoding for you? So instead of me trying to figure out which pin to jump, I put a binary number on the input and it turns on the right segments for me. So yeah, so we got a guy called a 75. By the way, what we usually do is we put one resistor per LED. Now you think about it, these guys here, roughly they drop about 2 volts. So if I was going to put a resistor in here, okay. By the way, we'll look this up, but usually the voltage drop, if we don't know it, we think it to be around 2 volts. But actually it varies with color. And normally we run these at about 15 milliamps. So it means if I was going to power the LED up on a 5-volt supply, I would come up here and I would put a resistor, right? You understand? And then this is, I would, if it's a common cathode, then I'm going to turn it on with the cathode. And then over here, the anodes will be connected to plus 5 volts. This guy drops 2 volts, so what would the resistor drop? Got to drop all the voltage. Got 5 volts supplied. Resistor's dropping 2, so okay. So this guy here dropped 3. It's going to drop 3 at 15 milliamps. So the power required by that resistor would be equal to V squared over, 3 volts at 15 milliamps. So let's do it that way. So power needed resistor would be equal to 3 times 15 milli. So what would be the power for that resistor required by that resistor? What's that? 45 watt. 45 milliwatt. So what size does that resistor have to be? Little bitty, right? Little bitty. Y'all seen a quarter watt resistor? Have y'all seen an eighth of a watt resistor? Have y'all seen one and have y'all held one? Let me go get an eighth of a watt resistor. Not in this form right here. So this is an eighth of a watt, which is 125 milliwatts. Surface mount can be a lot smaller, or they can be integrated. So what we do, and I don't have any SIPs, but I do have some DIPs, is what they do is when we got to have a lot, so we use a lot of pull-up resistors, right? Pull-up resistors and pull-down resistors. These guys are just pulling down, the output of my gate for a load can be a maximum of about 16 milliamps, which means I don't even need a quarter watt resistor, an eighth of a watt for that. My output for a high for standard TTL is around 400 microamps. I don't need an eighth of a watt for that. Y'all understand? I can actually do smaller. Well, the smaller the resistors, sooner or later, what they're going to do, they're going to integrate them in a pack. So we have what we call resistor packs. Now this is a dip. This would probably be better to do with a SIP. So if you look at an IC and it's a weird color like blue or something like this, then odds are these are not integrated circuits. These are resistors. That's all they are, resistors. And how do you think the resistors would go? Well, they're going to just go straight across. So I have a resistor. This is a 16 pin, so I got a resistor between pin 1 and pin 16. You don't power up resistors, right? You understand that? They're just resistors. So this is a resistor pack. We have what they call SIPs. So these are DIPs. What would you think a SIP would be? So if a DIP is a dual inline package, what do you think a SIP would be? If a DIP is a dual inline package, what would you think an SIP would be?
Good gracious, guys. A single inline package. So these guys are going to stand up on their end, and all the pins come out one side. I thought I gave y'all good enough hint. SIP. Yeah, I'm sorry. DIP. SIP. That's what they are. That's what a SIP is. You'll see a lot of these, and what they'll do is they'll come over here. If they're pull-up resistors, inside all the resistors will be done like this, and then they'll come over here and they'll have like this, and then they'll bring a pin out. So what you can do with these is and then you'll have all these pins right here, and that would be what a pull-up resistor would do, right? You understand? So these are SIPs. So you'll see a lot of SIPs on the integrated on digital circuits. These are going to be just pull-up resistors, and so they occupy little space, right? You understand this? And then you're going to have DIPs. For 7-segment displays, since we've got to have one resistor per side and there's no common, then what we'd use here is we'd use a DIP. But these are called resistor packs, and you'll run into a lot of these in digital because we're always pulling stuff up. SIPs, we use it. Pull-up resistors and pull-up down resistors are usually SIPs, and then resistors are usually going to be DIPs. Because we're not dealing in digital, we're not dealing with a lot of current, right? You understand? We're dealing with ones and zeros. So this is a 330 ohm resistor. So I don't know if I can get my meter up here. I think I can lay it like this, and then I'll turn it on. Put it on the 400 ohm scale, and you see when I measure across from here to here, measures 331 ohms. But it don't measure there because that's a different resistor, right? So these resistors are in here, just across each other. You okay? Does that make sense? So instead of using one resistor, so what happens when I use one resistor? Well, every time I turn on a segment, all the other segments do what? So what we normally do is we put one resistor per segment. And we put it in the control pin, not in the power pin. We put it in the control pin. That makes sense? A 330 ohm is usually what we use. 330 ohm or 470 ohm. You see those used a lot. Hey. By the way, these things are, some of these things are numbered kind of strange. Oh, here they are. So I'll pass these around. When you look at the value, you'll see 331. And don't pay attention to the G. Some of them are labeled. I want y'all to see this. This is one method we use to label electronic components. So y'all look on there. 331 on there somewhere. What do you think that's telling you? 3310. So basically, it's kind of like a color code without the colors. So 331. So that's 33 and 10. Right? You understand? No, not red. Orange. This would be an orange brown if it was a color coded resistor. Remember, it starts at 0, Kareem. Yeah, there's a lot of them. I was in the Navy, so I'm not going to tell you the way they taught us the color code. Huh? No, I didn't. Of course, I don't even think about it anymore. But anything in the military usually got profanity in it. We were in the Navy, so our A school, our instructors were both Marines and Navy people. The Marines were a lot more colorful than the Navy people.
We had one Marine that told us how he got his dogs to not like people in the Navy. It was funny. They were funny. We had one guy. Y'all remember the old overhead projectors where you put the transparency on there and you had the big old class thing? We was in a class with a Marine instructor one day, and we was up there talking, and an ant ran across the display. And he looked over there he had this pointer, and he was up there, and also he ran across there again. He ran across there again, and he took that pointer and went, "Flap!" And the whole thing just shattered right in front of our eyes. It was so funny. We laughed about that so long. And he said a few choice words too. That's Dakota's got 47,447. Let's look at my 7447. So that should be in our data sheets. This is one. We got a 7448. A 7448 is a common cathode decoder. A 7447 is a common anode decoder. You'll probably run into the 7447 more than you do the 7448. So the common anode displays are a lot more prevalent than the common cathodes. Oops, wrong guy, sorry. 7447. So this guy here, the way they got here, it's got pins labeled A0, A2, A3, A1, A2. So that's your binary inputs. Then it's got outputs labeled A, B, C, D, E, F, G. You'll see that? So that's what you'd hook it up to your watt, to your segments. They got bars above them. What does a bar mean? This is another way we use, that means they're low active. So this guy drives a common anode display. And what we would do, I can't do it on here, guys, but we would put a resistor in each one of these lines. And that's where we'd use our watt. We either use resistors, or normally we use resistor packs. What do you think LT would be? Just take a guess. LT. So I'm looking at pin 3, LT. It's low active, that's true, but what do you think LT means? What would we like to do? Huh? Close. We're not dealing with loads, we're dealing with lights. Lamp test. Yeah, so if I come over here and I bring lamp test low, then all the outputs would go low, and your display should display an 8, right? That makes sense. Ripple blanking. Ripple blanking is a term. So what they do a lot of times when you look at these displays don't have to be fast. Don't understand that. So instead of using 4 data wires for all your displays, for 4 for each. So let's say so if I look at this frequency counter, it's got 1, 2, 3, 4, 5 displays on it. Well, it's using a 7447 to decode it, right? You understand that? So that means that would have to be 4 inputs for every display. But when you look in there, there's not 4 inputs. There's 4 inputs being shared by all of them. But what they do is they multiplex. They allow multiple signals to share the same line. So what they'll do is they'll blank. In displays, when we blank, it means to turn off. Have you ever took a video of your like your cable box or something like that, and it looks like the displays are blinking? Well, that's what it's doing. You're actually seeing the multiplexing. So if you ever take a picture of it, and sometimes you'll take a picture of it and only one letter, you're looking at it and all of them's lit, you take a picture of them, only one display's on, right? Because that's what they're doing. They're multiplexing. So what they do is they blank 4 of them, and then they put the data on for 1 of them. Then they'll blank it and then put it for the next. Then they'll blank it and put it for the next, right? Y'all follow me what I'm saying? And what it's doing is it's doing it so fast that your eyes do what?
your eyes see them on all the time, but they're not. So do that. Snap a picture of your cable box and stuff like that, and see if you only see like one or two of them on, then it's because that's multiplex. If all of them's on, it means it's not multiplex. So that's what we can do with these ripple blanking. Is we can do what? We can turn this one off and turn another one on. Put the data on for that one. Turn this one off and then turn the next one on, and we just go through the display. These right here are multiplex. So ripple blanking in, ripple blanking out, and of course ground and power. But this is a decoder. I don't have it hooked up right now, but it's going to look like it takes a lot of wires. But all I need to do is just do what? All I need to do is just put a binary code into this thing, and it determines which segments to turn on. So let's go back and look at the truth table. I know y'all need a break, guys. There's makeup, by the way. Do y'all care about that? But it's nothing but what? Nothing but ands, nands, and yeah, it's the 5 basic gates. And here's the truth table. So let's look at it. So here, we're not doing lamp tests. We're not doing that. I put all the lows on. So A, B, C, D, 0, 1, 2, 3, these are all lows. So it's going to turn on the A segment. I can't draw on this. So it's going to turn on the A segment. Where's the A segment at? It's across the top, right? Can y'all see that? Yeah, because it's low active. We're using common anodes. That gets people confused. So common anodes, we turn those on with lows. Common cathodes, we turn those on with what? Highs. So this says A is going to be on. It says what? B is going to be on. So A is on, B is on, C is on, D is on, E is on, and F is on. So what's it going to display? It's going to display a 0. Well, what did I put into it? I put a 0, right? I'll get it the right one. So I put a 0 in. So that's a binary 0, right? You understand? And it turned on a what? A 0. This is a 1. Notice I could go through these segments, and what would it distance? So here it's only going to do the B and C, and that's going to be a what? That's going to be a 1. We could trace all these through. I put a 3, it's going to display a 3. I put a 4, it's going to display a 4. I put a 5, it's going to display a 5. I put a 6, it's going to turn on the segments to display a 6. 7, 8, 9. What if I put an A on there? Well, it's going to go crazy, but it's going to decode something. So this says if I put a binary 10 on there, it's going to display this. If I put a binary 11, it's going to display this. If I put a binary 12, it's going to display that. If I put a binary 13, it's going to display that. If I put a 14, it's going to display that. If I put a 15, it's going to turn all the segments off. So I've seen people use this for a hex decoder. But what they do is they memorize, this means an A, this means a B, this is a C, this is a D, this is an E, this is an F. I've seen them used. They don't use them often. What the compatible computers do is that every time it gets a fault, it sends an error code down its bus that you can plug stuff in. We used to have what they call a postcode card that some of your fancier motherboards, it was built in. I don't know if y'all remember these, but it had two 7-segment displays down there that if it failed, it would give you a code and you could look it up on a chart. Most of your motherboards didn't have that. So what we did is we had a postcode card that we could stick into the expansion slot, into one of the slots on the motherboard that would capture these error codes for us. And we used to teach how to make them, by the way. We used to make them here, by the way. I tell them how to make them. To save money, we didn't use you can get like a 9368, which is it's a hex decoder. We use 7447s And of course, the codes they sent out were binary codes, but people don't understand the binary codes, so we'd display them in hex. And we use these guys, and all you had to do was figure out what an A was, a B was, and a C code. Of course, we don't see that much anymore because most of our computers now are unrepairable. Because most of our computers now are considered to be consumable. So even though you pay a lot of money for cell phones now, you know, you'll pay a lot of money, right? You understand that? So now most companies don't give them away anymore. You pay for them as you go along. But and how much they cost now? Up $500-600, right? For $700. So all y'all take out insurance on them, right? If you don't, mine I always downgrade, so I'm always one below. So in fact, I'm two below now. I got a 5F. Yeah, well, that was the last time mine went bad on me, and I upgraded. That was all that was available. The 5 wasn't even available. So I had to get a 5F. And it does everything. I'm not planning on upgrading anytime soon. Well, that's what happened to my 3. It finally wouldn't charge anymore. My last 3, my other 3, the first 3 I got, I went swimming with it. Huh? Yeah, don't bother me. Mine does what I need it to do when I need to do it. Now it's getting very popular to go with these big old things now, you know. Okay, guys, y'all take a break.